So I'm talking about special PET scans seeking symmetry in quark-gluon plasma. So this is the outline of my lecture. First, I will introduce special PET scans, and then I will mention why we need to study quark-gluon plasma, and then what is the symmetry I'm talking about. And then I will talk about our experimental approach and the results, and finally come to my summary. Before I go to any of this, I would like to introduce elementary particles related to my lecture today. So those are electrons and quarks. So we know that 3 quarks can form protons and neutrons, and protons and neutrons can form nucleus. Electron and nucleus can form atoms. So those are really elementary particles. And there are 6 flavors of quarks with different masses. And here just shows you the 6 flavors of quarks. The size of the ball represents the mass of the quark. And you can see among those 6 quarks, we call it U quark, or you call it up quark and down quark are the lightest one compared to the other 4. And compare the mass of the light quark compared to protons, and this is protons, and you can just immediately ask the question, how can 3 light quark, such light quark, can form a proton mass? I will go to introduce this later on. And the other one, if you look at, this is actually electron mass. So electrons are even tiny compared to the light quark. Just a few facts for the elementary particles. So electrons interact with matter through the exchange of photons. And I want to mention that electrons and the photons, they do not interact with matter strongly. And this is actually quite important. And that's why we can say we can use electron-positron as a tomography tool. And quarks interact with matter through the exchange of gluons, and this is strong interaction. So later on, when I say positron, which is nothing but antimatter electrons, so the property of positrons is basically the same as electrons, except, for example, the electric charge is different. So later on, when I talk about antiquark, it's antimatter quark. So now, go to my real lecture. So I mentioned I will use special PET scan, then you will ask the question, so what are the traditional PET scan? So PET represents the positron emission tomography, and this technique has been widely used in hospital, for example, to generate picture of human being. And here just shows the PET actually use electrons and the positron annihilation here to create 2 back-to-back photons. And these 2 back-to-back photons and then measured by these detectors. And the information are then sent to electronics and sent to the computer. And at the end, you can obtain the image of a human brain, shown here. So for the special PET scan I'm discussing here is basically electron-positron tomography. And here shows you the cartoon. In our method, we detect electrons and the positron pairs from quark and antiquark annihilation in the quark-gluon plasma. And as I said, electrons do not interact with matter strongly. And that's why electron-positron pairs, they are penetrating probes and can provide information deep into the system and early time. And using electron-positron tomography, we would like to study symmetry of quark-gluon plasma. And I'm going to introduce symmetry later on. So why we need to study quark-gluon plasma? And quark-gluon plasma is believed to exist in the moments after Big Bang. And at the Brookhaven Lecture Lab, we are trying to create quark-gluon plasma using high-energy heavy ion collisions. So by studying the properties of quark-gluon plasma, and will help us to understand the early universe. And in the quark-gluon plasma, there are light quarks, up-down quark, as I mentioned, those are lightest one. And there are gluons, and the system has chiral symmetry. So now, in the next few slides, I will talk about chiral symmetry and its breaking. As I said, in the early universe is very hot and dense, and there is a chiral symmetry. And if you look at this plot, and this plot just shows you potential, the z-axis is potential as a function of x and y. And the potential is just using this formula. And the potential has a ball-like. You can imagine if you just throw a ball in this potential, and this ball will find its most comfortable place or most stable place in the center of the ball. And now, if you look at the ball plus the potential, and it's symmetric. When the early universe evolved into the world we're living in now, which is cold and dilute, and the potential actually changed. Instead of a ball-like potential, now it's ball-like potential, now it's actually like Mexican head. It's like this one. Mathematically, it's only minor difference. It's just add a term here. But the shape is dramatically different. So imagine if you now throw a ball in this Mexican head, what will happen? It will choose its most comfortable place or most stable place in this valley. And now, if you look at the ball plus the Mexican head, you find there's no symmetry. The symmetry is breaking. So this is a spontaneous chiral symmetry breaking. In a physics language, the most stable position has basically non-zero value. It's not in the center of the potential, means there's non-zero value in this axis. In physics language, that means sigma field is non-zero. And the particle actually interacted with sigma field to obtain mass, and this is actually quite similar to Higgs mechanism. Like elementary particle interact with Higgs field to obtain the mass for the elementary particles. So now, a little bit detailed, more microscopic picture for the chiral symmetry breaking. So in the microscopic picture, the left-handed quark and right-handed antiquark, they attract each other through the exchange of gluons, and then quark condensate is formed. And this generates 99% of visible mass in the universe. And this process is actually quite similar to the process of generating superconductivity. For this case, at low temperature, the electrons attract each other through the vibration of the crystal, and electron condensate is formed, and this generates superconductivity in the matter. So now I just summarize what I said in this slide. I mentioned in the early universe, which is hot and dense, there's a chiral symmetry. The potential looks like a bowl. When the early universe evolved into the world we are living in now, which is cold and dilute, this is spontaneous chiral symmetry breaking. The potential change like a Mexican head. So in the quantum plasma, we created a Brookhaven National Lab. We believe it's hot and dense. And we can ask the question, and this quantum plasma is as hot and dense as early universe. Is chiral symmetry restored? From theoretical model calculations, when you go to higher temperature, the quark condensate will disappear. So chiral symmetry is restored from theoretical model calculation. Then the next question is related to our measurements, is do we have experimental observables? So now I'm going to introduce experimental observables. As I said, spontaneous chiral symmetry breaking gives us 99% of the visible mass in the universe. It also gives different masses to different particles. Here we talk about two special particles. It's Rho and A1. These two particles are resonances. So that means their mass value is not a fixed number. It's not like a proton. Their mass value is changed. So their mass has a distribution. And here just shows you the mass square distribution for these two particles. And this is Rho, and this is A1. And data points represent measurements. And the curve on top of data points represent theoretical calculations. For example, just from the Rho particles, from the measurements include this peak structure. This is like represent the ground state. It has this smooth function. This is represent continue. And this is another bump here, represent excited states. And theoretical calculation only include the ground state plus continue. So you can see in the mass square 223 GeV, the data is above the curve. So from this one, you see spontaneously chiral symmetry breaking, these two mass distribution for these two particles are really very much different. So when the chiral symmetry is restored, when the temperature is high enough, chiral symmetry is restored, we would expect the mass distribution of these two particles are modified. It's modified in a way that at the end, the mass difference between these two particles disappears. That means their mass distribution completely line up with each other. So then the question is, can you experimentally measure that? Experimentally measure this particle, A1 particle, is very challenging and difficult. So instead, we actually focus on to measure this Ruan particle. And basically study the modification of its spectral function. And this is, again, you see it's a vacuum-like, it's a peak structure. And we want to see whether at some point the Ruan spectrum got modified and it's got broadened, and at the end, we want to see whether this kind of peak structure disappears. And if the peak structure disappears, that means if I just give you a very smooth function, if I ask you, do you see a particle? You probably will say, no, I don't see a particle. And that's what we want. That means this particle is completely melted. And this would be the signature of chiral symmetry restoration. So now, I just put my physics interest for this lecture here is I would like to study quark-gluon plasma and its chiral symmetry restoration using electron-positron tomography. And most importantly, I would like to identify the signature of chiral symmetry restoration and basically see that mass distribution become broadened, and eventually to see whether we can observe the mass peak structure disappear. So that is basically the motivation for the experiment. So now, come to the experiment. So we use relativistic heavy ion at the Brookhaven Collider at the Brookhaven Lecture Lab to do this one. And here just shows you the complex of RIC. We have a LINAC and just different parts, LINAC, booster, AGS, and this is a RIC ring. And the accelerator can really accelerate the golden nucleus up to very high velocity. And you can see this is 99.995% of speed of light. So it's really very high energy. And here, I would like to show you a go-go nucleus collision animation movie. And you can see at the beginning, this is just two golden nucleus, they collide and pass through each other, and you can see very hot dense matter is formed, and then particles got emitted, and the whole system is actually expanding, and basically the system got more cool and diluted. And eventually, you see a lot of points here. That means a lot of particles here. So the question would be, can we measure those particles? So we use basically a star detector to do that. Because I'm from a star experiment, so I only present star results. And for this study, the main detector used a time projection chamber and a tunnel flight detector. Later on, I'm going to introduce muon telescope detector as well. If you have a chance in summer Sunday, in 10 days, you can actually go to look at a star, and you will find it's really very big. It's about 10 meters tall, and it's also along the midnight direction, it's also about 10 meters. So it's quite big. For the time projection chamber, it's the second largest device of its kind ever built. And you can think it as a three-dimensional camera to take photons of the accretions. And the whole detector are actually operated, especially time projection chamber operated under the magnetic field. The magnetic field along the midnight direction, and this is the midnight direction. So you can imagine, if I charge a particle going through the magnetic field, what will happen? So it will bend. So through the bending, we can measure the momentum. And also, when a charged particle going through the gas of time projection chamber, it will ionize the gas. And we can measure the ionization energy loss. And through the ionization energy loss and the momentum, we can identify different particles. So as I said, time projection chamber, you can think it as a three-dimensional camera. So here just shows you one photo taken by this camera. And these are head-on go-go collisions. And for this plot, the binary direction is perpendicular to the plane. For this plot, the binary direction is in parallel with the plane. And these are actually the same collision, the same event. And you find we have lots of trajectories. And initially, we only have less than 400 particles, less than 400 protons and neutrons. At the end, we have thousands of particles, and this is really just due to Einstein's E equal to mc squared equation. So 70% of the initial energy actually downward into the system, and those energy convert into particle production. So then you ask the question, because I'm talking about electron-positron tomography. So you ask the question, are those electrons, are positrons? What are those? And can you find electrons from those trajectories? So here just shows you the plot. Here shows you the ionization energy loss versus momentum identified by time projection chamber. From this plot, you see a lot of points. One dot or one point represent one trajectory I just showed you before. And here you also see the red one represent higher statistics, and the blue one means lower statistics. So from this plot, you see several bands. Electron bands are here. So first of all, you find electrons are really fewer compared to others. Secondly, you see at the different momentum positions, electrons are just mixed with all these other particles. For example, here is around 0.2 GeV, and here about 0.6 GeV. So we can conclude electrons have a lot of contaminations from others, are very difficult for us to identify, and we need new experimental tool to do that. And the new experimental tool comes from the new detector and the new detector technology, and this is actually multi-gap resistive plate chamber technology. And there are two advantages for this one. Low cost, this is probably the most important one, and also the very excellent timing resolution. The timing resolution is less than 100 picosecond, and picosecond is 10 to the minus 12 second. So you can just think how precise it is. And I actually got a chance to get involved into this MRPC detector technology when I was a PhD student. So in 2001, I built about 12 these kind of modules based on MRPC technology. And those in my home institution that time is actually in China. I was a PhD student. And those modules actually sent to Rice University in the United States. So they put those modules in the tray box, shown here, and then they sealed this tray box. This is a basic gas box. And the whole thing, and then delivered to Brookhaven National Lab for further test. And after that, it's installed at STAR in 2002 and 2003. And that time, we call it, this is a prototype tray. It's not a final tray yet. So then you ask the question, why this detector technology is cheap, and why it gives you such excellent timing resolution? So here I would like to show you structure of these detectors. It's cheap, it's just because the material to build this detector is so common. We use glass and fishing eye. Fishing eye are really those knives for fishing. So it's something very common. And here shows you structure. And we just basically put a stack of glass all together. Between each glass plate, we use fishing eye to separate them. So fishing eye serves as two purposes. One is to support the glass. The other one is form the gas gap. So because the material is really so common, that's why this device is very cost effective. And why it can give us very, very good timing resolution? I give you a cartoon here. For the MRPG detector technology, we have 6 gas gaps in total, and here just for 1 gas gap. So you can imagine when a charged particle going through the gas, again, there is ionization process. So electrons and the positive ions will be generated. Under the electric field, so we applied high voltage to the detector. So under the electric field, the positive ion and the electron will drift toward an opposite direction. During the drifting process, an image charge will be generated in the readout strips in the electronics and connected by our electronics, basically. And from this one, because our gas gap is so thin, it's just a 220 micrometer. So the gas gap is really very, very thin. And also because the electron drift velocity under this electric field is actually quite fast, it's quite high compared to other gas detector. So you have a drift distance, you have the drift velocity, you can just calculate drift time. So the drift time is a very small number. And these actually give us a very good timing resolution. So based on this excellent timing resolution from tunnel flight, and also from time projection chamber, it can measure the path length. You just see those trajectories, right? We can actually measure the path length. So you divide by path length by the tunnel flight, what do you obtain? You obtain velocity. Here just shows you inverse velocity versus momentum. The velocity is in the unit of speed of light. So unity here just means this particle has a speed of light. So here shows you can see again for this plot, each point or each dot just represents one trajectory you see the picture taken by time projection chamber. And again, the red one means higher statistics, and the blue one means lower statistics. And from this one, you see several bands, and several bands just represent different particle species. And for each band, for example, this one for protons, you also see a curve. This curve just using the formula here. So we put the proton mass here, you can obtain this curve. If detector resolution is 0, it's perfect and ideal, but of course it's unrealistic. You will see a curve rather than a band. So you see a band, this is really just resolution effect from different detectors. From this plot, you see the electrons has a velocity very, very close to speed of light. So then if we cut on the speed, we choose the speed very close to speed of light, just using this card, and we plot ionization energy loss versus momentum again. So what do you see? You see these are electron band, and these are hadron band. This is before we have tunnel flight detector. This is after we have tunnel flight detector. And you can see after we use the information from tunnel flight detector, we get very, very clean electron identification. These two plots are all from that prototype. So I think the prototype is really quite successful. And from the successful experience of that prototype, I think it's really led to a real project, which is we now call it tunnel flight detector upgrade at STAR. And this is just myself in 2007 when I joined Brookhaven as a Golden Hub Fellow. And on the table, you see several trays. These are just 1, 2, and 3. On the other table, there are another 2 trays. So in total, there are 5 trays. And those 5 trays just prepared for the run in 2008. And for the next 2 years, we finished the tunnel flight detector upgrade. So in 2010, we have the full system. That means 120 units of this kind of thing. So now, with the full tunnel flight detector coverage, that means large acceptance, with clean electron identification, I just show you. Now we can say we have an electron-positron tomography tool ready. So now let me just show you results. The first thing, you will see a lot of a picture just like this. The first thing you will ask is, how can you get a mass from two particles? It's an electron and positron is two particles. How can you get a mass? It's because these two particles, they have energy. You can treat these two particles as a system that has energy. As I said earlier, Einstein has energy equal to mc squared. So from that energy, you can get a mass. That's why we can get a mass from electron-positron pair. And then the next question you ask, I would like to study electron-positron pairs from quark-gluon plasma from hot dense medium. Then you ask, if you have no contribution from the hot dense medium, how does it look like? So this plot shows you how does it look like. So the red solid curve represents the electron-positron emission mass spectrum without any hot dense medium contribution. So for example, the quark-gluon plasma, as I already showed you, it will expand and later on cool down. So this one is really just shows you the contribution from the dilute and the cold matter. So the idea for our measurements is we have our measurements and we compare our data points to this solid curve to see whether there is any extra contribution, right? Any extra contribution will represent the hot dense medium contribution. So this shows you the results from our top energy 200 GeV gold-gold collisions. And the data represented by those circles. And the solid curve, again, as I said, is those from those dilute and empty space without any hot dense medium contribution. For all these different components are shown by different curves here, but I think you do not have to worry about that. So if we compare our data to the solid curve, what do you see? You just find their data is above the curve in this mass regime. So those represent the contributions from hot and dense medium. So from now on, I will just call it hot contribution. So those are hot contributions. This is the first big step. You first identify hot contribution, and then you start study them. So RIC is very flexible and versatile. So it not only gives us top energy, like 200 GeV, it can go to the low energy, like 7 GeV. It's a factor of 30 difference, and it's actually truly remarkable. And the staff, our experiment fully take advantage of this. So we can measure the electron-positron emission down to the 19.6 GeV. And here shows you the data points. This is for 200 GeV, 62 GeV, 39, and 27, and 19.6 GeV. So the circles, all the circles represent measurements. For each energy, we scaled by different number so that you can see them clearly. So for each energy point, you also see a yellow band, not yellow band, the gray band. And those gray bands, again, are those contributions from cold and dilute empty space. So if I compare data points to the curve, you always find that the data is above the curve. That means there are hot contributions all the way down to 19.6 GeV. And how does it look like? As I said, find the hot contribution is a very important first step, because first you have to see the signal. Then you study the signal in detail. So how does it look like? So those represent the hot contribution. So does it look like the very broadened mass spectrum as predicted by theoretical models? Or does it look like a vacuum-like? This means just like a cold, empty space. It turns out, if we actually add those broadened contribution on top of the solid curve I already mentioned, and the total contribution become an orange band, and now you see, you compare the orange band to the data points, you find the orange band are on top of the data points for all these energies. So that indicates the observed, now we can say this is what we are observed. So observed hot contribution are all broadened. So now let me look at the hot broadened contribution in a little bit more detail and look at the energy dependence. So here just shows you the energy dependence. This is for 19 GeV, 39 GeV, 62 GeV, and 200 GeV. From these plots, you find they are very much similar, right? The shape is very much similar. The amplitude is also very much similar. Why is that? So what kind of a quantity, physics quantity, actually drive the broadening of the spectra? Because the energy differs by a factor of 10. It's a dramatic difference. It turns out one physics quantity actually really drives the broadening of the spectral function. But I'm not going to say what kind of physics quantity it is. You have to believe me. So that physics quantity actually does not change from 19 GeV to 200 GeV. So that's actually very important. And we find if we actually go to the low energy, for example, go to the 7.7 GeV, this is now is almost the lowest one Rick can do. And that physics quantity increased by a factor of 2. So naively, you would expect this function, this mass spectral function, emission pattern, will get even more and more broadened. At some point, we would like to see this kind of peak structure completely disappear. As I said, if you just see a smooth function, what do you see? You see, I see nothing. I see no particles. That would mean that resonances, that particle is completely melted. And this would be the last piece of evidence for the chiral symmetry restoration. To go there, we actually have to have several upgrades. Our star detector, we have our detector upgrades, but most importantly, we need electron cooling upgrades from CAD, from Collider and Accelerator department. Electron cooling, you can imagine you just shoot electrons to the Rick ring, and this is to decrease the size of the bunch, and this actually make, for example, the beam, the golden nuclear spin, the bunch intensity increase, and therefore the accretion rate will be increased. So here just shows you the luminosity, but luminosity you can think it just as accretion rate. So accretion rate as function of energy. And this is what we can do now, those squares. This is down to 7.7 GeV, 11.5, and 19.6 GeV. And if you compare, this is the projection for 4 years later, for 2018. This is a projection for 2019. And you find this is already with electron cooling upgrade. With that upgrade, the accretion rate can increase by a factor of 10. So what does it mean? It means if now I take a data for 10 weeks, by that time, in 5 years later, I only need 1 week. And then we have the same quality of the data. So this is the most cost-effective way to do experiment. I think study the chiral symmetry restoration in the hot dense matter is very important, because it's when the hot dense matter evolved into the world we are living in now, the chiral symmetry is spontaneously breaking. As I said, this give 99% of visible mass in the universe. So how important is that, right? So I would just say it's so important that from all over the world, and many scientists are trying to work on this topic. And here just shows you from low energy down to SPS energy in Europe, and also Phoenix collaboration at RIC, I didn't mention earlier on. And we also have a Large Hadron Collider. They also have an experiment trying to look at the same thing. And you all probably know that at this collider, Higgs boson was just discovered. And this is also down to low energy. In Europe, we also have Asia. This is from Japan. So this is really worldwide interest topic. So next, I would like to mention one more topic I'm working on. So electron-positron can be emitted from the quark-gluon plasma, and the photon can be emitted as well. Probably you know that from the sun emission spectrum, that means measure the energy distribution of the photon. We can get the temperature of the sun, right? So we would like to do the same thing. We would like to measure the energy spectrum of photon, but those are emitted from quark-gluon plasma, and we would like to get the temperature of quark-gluon plasma. So here just shows you the results. This is transverse momentum, but you can just think it as energy, photon energy. And this is a production of photons divided by its energy and divided by each beam width. So for each measurement, you have a range. You just divide by that range. And the circles basically represent our measurements. And also, I think for this type of measurements, the first thing you ask is whether you really see those hot dense medium contribution, right? So this one, the green curve, is actually represent those contributions from cold and dilute space. And you can see the data points is significantly above this green curve. That means there are hot contributions, right? And then we add those hot contributions from theoretical models, and you can see it can describe our data quite nicely. So as I said, from the sun emission spectrum, we can know the temperature of the sun. So here just shows you the sun emission spectrum, and this is in wavelength, nanometer scale. From that, you can convert into energy. That means photon energy is only a few electron volts. And from quark-Gluon plasma emission spectrum, the photon energy can achieve a few 10 to the 9th electron volts. You just compare these two numbers, and you know how hot the quark-Gluon plasma compared to the sun. So indeed, the quark-Gluon plasma we created here is the hottest matter in the universe. And here I only put a few trillion degrees Celsius because I'm really realistic, trying to be realistic, because our measurements here has big uncertainties. So this will be further improved in the future. And by that time, I hope I can say this is really what kind of number here I put instead of few. So now I'll come to my summary. I hope I give you a picture. We are using electron-positron tomography trying to study the symmetry of quark-Gluon plasma. We actually identified that for that particle, special particle, we find the mass distribution really get broadened. And this, I think, is already a strong indication of color symmetry restoration. But to find the absolute evidence, we really would like to see whether at the sun energy, this kind of a peak structure just disappear. And if so, and that would form the last piece of evidence for the color symmetry restoration. And at the end, I would like to mention the muon telescope detector. This is, again, one detector upgrades, and based on the MRPC detector technology. And for this detector, what I want to do is I would like to use muon and antimatter muon pairs. And you can think that this is actually very similar to electron and positron, because compared muon to electrons, the properties are almost the same, except the muons are much heavier. So that's the only difference. And using these pairs, I would like to study the melting of heavy particles. As I said, using electron-positrons, I find that particle got broadened. The mass of that particle is very similar to proton mass. And from this device, I want to study the heavier particle, which has a mass like a factor of 5 to 15 heavier than the one I just showed you. So with that said, finally, I would like to thank my collaborators and about 600 people from 58 institutions and 13 countries. And especially, I would like to thank my students and postdocs, because without their efforts, without their talents, I just cannot simply stand here. And here, finally, I would like to thank Department of Energy, Office of Science, for supporting me with Early Career Award. So that's it. Thank you.